Hello, everyone, and welcome to one more Plane Time show. My name is Diego Alfonso, and one of the hosts for the Florida Aviation Network, broadcasting live and in the clear from our studios in Oviedo, Florida. Folks, if you have seen our guests before, you know more or less what to expect. However, if you're tuning in for the first time, you are in for a treat because this presentation is full of goodies. I'm telling you, full of goodies. What I'd like to do now is to share his extensive and impressive background. And I'm going to read it because I don't want to miss a bit here. His name is Dr. George Bartuska. He was born and raised in South Bend, Indiana. He was stationed at the North Island Naval Air Station. He was also in the USS John F. Kennedy aircraft carrier, and he did a Mediterranean tour during that time, and he's also an aviation mechanic. He attended Purdue University in West Lafayette, Indiana. He obtained a BS in engineering and economics. He works as aerospace test engineer for Bendix in South Bend, Indiana for 10 years, and at Martin Marietta Aerospace in Orlando. He was an engineering consultant for about 15 years. He retired in 2008. He taught high school science for 12 years and retired in 2020. He finished his doctoral dissertation in 2021 from the Orlando University in emergency management and tropical meteorology. I always have a problem with that word. It had to be something with my accent. Meteorology doctorate. He now teaches weather for the U.S. Coast Guard, the USAF, Civil Air Patrol, Florida Aviation Network, and of course, he's a guest locally. We normally refer to him as the weather boy. However, I think a more suitable term is the weather expert man. Now, he's presenting you what I think we always wanted to know about hurricanes, but no one told us. Please help me welcome Dr. George Bartuska. Doctor,
thank you.
Pleasure to have you here. I know you're eager to get on the way here, and I'm going to let you do that because right now I'm transferring the controls over to you.
Okay, good. That's good because we have a lot to cover. First, let me say that normally a course on hurricanes or tropical cyclones, which is what they are, takes a whole day. FEMA's course is a day, my course is a day, but we all have a 1 hour. We all have a 1 hour presentation that we give, and I only have 30 minutes. So bear with me as I shrink an hour into 30 minutes. So if you think something is missing or was missing, that's why it's not here. Now, where is my monitor? First, I want to say, there really is no such thing as a hurricane or a typhoon. Meteorologically speaking, they are tropical cyclones. The reason I say that is because if you look on the internet for information on hurricanes and typhoons, you'll find some information. But the best information is under tropical cyclone. That's where all the research papers are. And up front, tropical cyclones are relatively rare because they require simultaneous preconditions to form. The necessary conditions for formations are common, but to have them all simultaneously is kind of rare. And right now, today on the 22nd of June, and a couple days before is a good example. We've had a system trying to form off the coast of Florida, and this morning the National Hurricane Center reduced the chances to 0%, whereas just a couple days ago they were looking at 30, 40, 40, 60%. Things have to be just right. And we have a term in meteorology that's a similar term in economics. It's the Goldilocks principle. If you remember, Little Red Riding Hood went into the Three Little Bears house, and one porridge was too hot, one porridge was too cold, and one porridge was just right. Well, same thing here with hurricanes like with tornadoes. The atmospheric conditions have to be just right. Now, what is a hurricane? I'm going to use the term hurricane now for most of the time because that's the term familiar to people in the United States. Although this is going out on the internet worldwide, you'll see I use other terminology as we go. A hurricane is a tropical cyclone. Tropical cyclone is a rotating vortex with organized deep convection, which means it has tall components to it, with a closed wind circulation about a well-defined center. If it isn't those things yet, we're not going to call it a hurricane. It's got to have maximum sustained winds of 74 miles an hour or 64 knots, and it originates over the tropical oceans and is driven primarily by heat transfer from the ocean, and we're going to go into that here and more. Now, there's 80 to 90 tropical cyclones worldwide. That number has not changed in 30 years. People keep asking, is the climate changing, is the global heating affecting this? The data so far shows there's no absolute correlation to hurricanes being more or being more intense, but that doesn't mean it isn't going to happen. The average size of a hurricane is about 300 miles. The length of the Florida Peninsula is about 350 miles, so just think about the length of Florida as an average diameter for a hurricane, but they can be bigger, they can be smaller, and they vary. All tropical cyclones are different or unique. Just as the forward speed is about 10 to 15 knots, and the expected path and intensity are difficult to predict. Now, having said they're all different, this is Hurricane Francis back in 2004. This is probably what we would call a typical landfalling hurricane. You can see that most of the hurricane force winds are impacting the coast, and as it went further across the state, it lost energy because it lost its source of energy from the water. And by the time it got to the other side of the state, it didn't have tropical force winds anymore. But this is Tropical Storm Charlie, Hurricane Charlie, that happened in the same year. And to meteorologists, it acted more like an F4 or F5 tornado. It was smaller, more compact, with larger, faster winds, and kept its tropical force winds for most of the way across the state. But every tropical cyclone or hurricane or typhoon, whatever you want to call it, is different. Now, hurricanes are dangerous. That's why we're talking about them. And as related especially to aviation, they cause major damage from storm surge, wind damage, rip currents, flooding, and tornadoes. Most people don't talk about rip currents because that's for people that are in the water, but we lose a lot of people to rip currents. Here's why we're here today. They can impact aviation in all kinds of areas. Okay, who's at risk? Anywhere you see the yellow area on this map is who's at risk of a tropical cyclone. So on the eastern coast of the United States, on the western coast of the United States, in Asia and Australia, anywhere that's 5 degrees or more north or south of the equator. And notice in the maritime industry, they refer to them as a tropical revolving storm. That's just a term we use. Now in the United States, who's at risk? This shows where landfalling hurricanes have come, but this map doesn't tell us anything. This is the map with the information. If you have an aircraft or if you're flying and you're anywhere this map is colored, you could be impacted. More so on the coast, but even as far inland as Chicago or Arkansas or Texas, because that 300-mile storm, when it goes onshore, it doesn't just stop being a hurricane. Now, where are the tracks? We're speaking here just of North America. This is about 40 years worth of tracks, but as I'll show in a little while, they don't all just come in and arc out. Now, when do they happen? Hurricane formation can happen anytime if there's warm tropical ocean waters of at least 80 degrees Fahrenheit in the water down to a depth of about 200 feet. The official hurricane season is June 1 through June 30th, but most tropical force storms form in autumn, say August, September, October, with September being the most likely time. Statistically speaking, the most likely day for a hurricane is September 10th in North America. Hurricane lifespan, average 10 days to 2 weeks. Some have lasted more than a month. Some have lasted less than a week. Now, we talk about the climatology of hurricanes. Once again, this is a reduced version of the seminar, but you can see by this illustration, most of the intense hurricanes are in August, September, and October, but it's June. We've already had our first one in 2024, and we have the potential for another one right now in the Gulf of Mexico. What do we need? We got to start out having hot water, 80 degrees or more. This is not the current map, but it's a map that shows at this time we're definitely ready to prime something. Now, deaths. Most people, when they think about a hurricane, the first thing they think about is the wind. Yes, they create a lot of wind, and that's impactful for aviation, but most of the deaths are from storm surge. Storm surge is the coastal flooding that comes in as a hurricane makes landfall. Now, what can it do? This is from Hurricane Katrina. You can see the structure on the left was before the hurricane. You look at the tree. On the right is after the hurricane made landfall. Next big problem is inland flooding. That hurricane is carrying 60 billions a gallon of water on average, and eventually it's going to give it up somewhere. High winds. Tornadoes have high winds, but they only last for seconds. Hurricanes have high winds that can last for an hour or two. So it's a different thing. And tornadoes. Hurricanes can spawn tornadoes. They tend to be smaller F1, F0 tornadoes, but they're still a tornado. Now, let's talk about the hurricane itself, the internal structure. A hurricane has an eye, which I'm going to talk about in a minute. But as you can see in the upper right-hand graphic, this thing we call the eye wall, or the inner cone, is the heart of the hurricane, as we'll see as we go here. Now, this is the plan view of a major developed hurricane. You can see that there are rain bands, we call them, the curved part on the exterior. And on the inside, you can see that there is the eye wall. This one has 2 eye walls. They can have 3 and 4 eye walls. When they have multiple eye walls, it simply means that they're about to intensify or detensify and then intensify again as the system is climbing. In addition, those rain bands on the outside are the first thing that people are going to encounter as the storm comes near them, in addition to the squall lines. Now, a little bit more specific. These relate to, I'm using the illustration of Hurricane Andrew in 1992. These spiral rain bands can be out 100 to 500 miles. They're intense organized thunderstorms. There are primary and secondary rain bands with thunderstorms, with heavy rain, strong winds, and tornadoes. Also under convective bands and straight hurricane squall lines, just like a squall line in the Midwest, a line of thunderstorms. The eye wall, which is the heart of the hurricane, made up of short segments of monstrous thunderstorms. That's all a hurricane is, a group of organized, monstrous thunderstorms and convective systems. The fiercest winds and heaviest rainfall are at 1,500 to 3,000 feet above sea level in the eye wall. Typical winds 115 to 150 miles an hour. In excess of 200 have been recorded. The ocean waves below the eye wall are 15 to 40 feet, which is why they typically sink any ship that ends up underneath them. And it says strong hurricanes often exhibit double eye walls with a moat, the different distance in between. We can see from this diagram that as we go up in elevation, it gets less intense, which is one of the ways that hurricane hunters can fly into it. But notice what I say there. When we talk about what the eye wall looks like inside the hurricane, the terms that are typically used are the stadium effect, which means it looks like you're in a stadium or a cereal bowl. It tends to taper out. Now the eye, most recognized feature of the storm. It's the storm's axis of rotation, typically circular, but not always, can be elliptical. And in that eye, the only reason that there is air sinking in, warm airflow, causing there not to be many or any clouds at all. Usually free of high clouds, clear to scattered low clouds. The eye can be 20 to 40 miles in diameter, exceptionally low air pressure. Most of the time, if there's a smaller eye, the storm is more intense, and the eye is one of the oldest phenomena known in meteorology. And there's another picture from the hurricane hunter looking at that eye wall. The eye is below in the middle of the picture, and this one happens to have some high elevation clouds. There's the overall hurricane again. Now, today, the way we analyze these storms is we use satellites, we use ground and airborne radar, we use aircraft and weather balloons and GPS radio zones and drop zones. But before all that stuff existed, the only thing we had was this, a recording barometer. And inside that barometer is a bellows unit. And I think he's going to put the camera on me. This bellows unit is exactly similar to the altimeter that's in your aircraft. This is the bellows unit from the recording barometer. This is a bellows unit from your barometer in your aircraft. So before satellites and radar, what we had if that hurricane went right over you is this trace, this track showing how low the pressure was, assuming the place that had the barometer survived and we could get the recording. Now, where does the energy come from a hurricane? It's the same for all weather. It's the sun's energy. But remember, the sun, from my previous lectures, the sun doesn't heat the air very much. It's at the wrong wavelength. So the sun has got to heat the water, and the sun is going to heat the land, which is re-radiated at a different wavelength to heat the air. In addition to that, the water is the dynamite of severe weather everywhere on Earth. It's the way we get the energy into the weather. Now, we imagine an imaginary parcel or blob of air. It acts just like a hot air balloon when it gets hot and becomes buoyant, less dense. I'm going to skip over this because I'm running out of time. But what happens is, as the air gets heated and it starts to rise, it'll go up to a certain level, and if it has water vapor in it, it'll reach a level where it reaches the dew point, and the air will condense and the water will start to come out of the air. We call that the saturation point or the dew point. In storm development, it's the lifted condensation level. If there isn't an inversion or it overcomes any other thing that would keep it from rising, it now starts to rise with positive buoyancy. It has reached the level of free convection, and it will keep going until it has used up all its moisture to what we call the equalization level. This, you may recall, is from my presentation on thunderstorm, but it's exactly what happens in a hurricane and what starts a hurricane. Now, wherever there's water and land, there are sea breezes generated. The unique thing about Florida is it has two coasts that are close to each other, and we get a dual sea breeze, one from the Gulf Coast, one from the Atlantic. And if there were no other weather systems, every day we'd have these combining wind systems coming in, and we'd have thunderstorms right down the middle of the peninsula of Florida. And that does happen, but we have other wind systems, high pressure, low pressure centers, and the jet stream that tend to mix things up. Now here's the standard life cycle of a thunderstorm that you have seen in your weather studies for becoming a pilot. Towering cumulus stage, the mature stage where we have rain, hail, tornadoes, etc. And then when the storm rains itself out, everything dissipates, and eventually that storm will dissipate right in front of your eyes. The difference with a hurricane is it's not going to dissipate until it runs out of hot water underneath it or it goes on land. It's stuck, so to speak, in the mature stage. Now, heat transfer. There's two kinds of heat transfer. Sensible heat transfer, like conduction, when you touch a hot stove or you touch the handle on your pot. That heat is moving from an area of from high heat to low heat. And that's part of the heat transfer that goes to a hurricane as it moves over hot water. But the other heat transfer is what's called latent heat transfer. When the water evaporates, like when you walk out of a pool, the water evaporates and you're getting cool. It's because the energy from your body was used to change that water from a liquid to a gas. Once it gets cooled down to the dew point, condensation takes place and it gives up that heating. And that's what causes the updrafts. and powers the storm. And think about it when you're blowing on food that is too hot. Where's that heat going? It's going somewhere. In the case of a hurricane, it's fueling it. Now, the other thing we need to form a hurricane is we need low wind shear, because high wind shear will blow the storm apart. In the Midwest, in supercells and thunderstorms, we need some wind shear, because if the storm is straight up and down, when it rains itself out, it basically cuts off its updraft. But for hurricanes, it's just the opposite. Now, where do these things take place? Notice I mentioned earlier, right at the equator and 5 degrees or so north or south of the equator, we don't have any hurricanes, because we need the force of the Earth rotation. We need the Coriolis effect to help the storm get going. So how does a hurricane really start? There's got to be a cluster of thunderstorms and a low pressure center, and the air that starts to move in. As air moves in on the northern part of the hemisphere of the Earth, it turns to the right. And if I have air coming in from all different directions being turned to the right, in between I'm going to be turning to the left. So the storm's going to be rotating counterclockwise. In the southern hemisphere, it's just the opposite. As the winds come in, they're going to turn to the left, and thus these storms rotate clockwise in the southern hemisphere. And now we see the drawing on the left, we have air coming in at the bottom and going up. Most people look at that and think, well, that air must be going up in the eye. No, that's going up right in the middle of the eye wall. That's what's happening. Just like a person who's a skater or other that's spinning, when you pull it in, the velocity goes up. And in this drawing, I call your attention to the one on the right. You can see in the lower part of that drawing on the right, the air's coming in at sea level, and then it's getting pulled up through the eye wall. Condensation is taking place, latent heat's being released, and it goes all the way to the top. And at the very top, some of it hooks around and starts coming down in the eye wall. Let's see if I'm missing. Now, this is one of the most reproduced images we have, from NOAA P3 aircraft of what's going on in the storm. I took that image and flopped it over so we'd have a cross section of a typical hurricane. Once again, you can see the air coming in at the sea level, then going up through the eye wall with a little of it coming back down. That's why the most intensive part of the storm is the eye wall. Now, life cycle of a hurricane. So it has to start somewhere. We have North Africa on the right part of this drawing. Tropical disturbance is caused by a tropical wave, or what we call an easterly wave, that basically creates a thunderstorm cluster. And if nothing else happens, there's some rain and that's it. But if we get some turning in there from the Coriolis effect, we start to develop a tropical depression. From that, if we get winds of 34 knots or more, we have a tropical storm. And when the winds reach 64 knots or 74 miles an hour, we have a hurricane. That can take a week to take place, or in the case of Hurricane Irma, it took place in a couple days. So it just depends, once again, on how much heat we have, what's the wind shear look like, and how much humidity is in the atmosphere. Now, one thing I don't want to forget to talk about, because we're talking about people with aircraft on land near the coast, is this idea of the right front quadrant of the hurricane. This hurricane, the exterior winds are blowing at 110 miles an hour around the storm, and the storm is moving 30 miles an hour. Well, if you're on the right side of that storm, you have to add that 30 to 110, and that'll give you 140 miles an hour. But if you're on the left side of the storm, and the storm is moving away, you subtract that and you only have 75 miles an hour. So you want to avoid the right quadrant of the storm, regardless of what direction it's hitting landfall. Now, I said all storms don't hook like that drawing showed. Tropical storms go where the planetary winds take them. Just the analogy is always a cork floating in a stream. The storm's going to go where the wind system goes. Storm tracks can wobble, turn, make loops, wiggle, curve back on their tracks, meander back and forth, and stop. The storm can stop, and that happened in Florida back in the 1950s. Here are some other tracks of cyclones out in the Pacific, of what we call typhoons. Now, one thing to keep in mind, in North America, we have about 5,000 miles of ocean between Africa and the southern part of the United States for the storm to grow. Out in the Pacific, we have 8,000 miles between the west coast of the United States and the areas of Japan and those areas be affected. So there's a lot more time for the storm to grow. So in short, typhoons that we call typhoons, tropical cyclones, tend to be a little bit bigger than hurricanes. Once again, this is a famous shot of something that happened during Hurricane Camille. You can see a 3-story apartment complex reduced to nothing. Now, aircraft. I'm running out of time. Okay, your aircraft. What are you going to do with it if there's a hurricane coming? First off, consider buying space in a hangar built since 1992. Hurricane Andrew in 1992 caused the American Society of Civil Engineers to up all the wind loading criteria. So if it's built after that, it hopefully will save your aircraft. If you have to tie it down outside, look for open space. Clear area without stuff that can blow into your aircraft. If you're in the area during the storm, tie the plane down upwind of anything that might blow into it. Securely latch the doors and windows, cover the engine inlets, pitot tubes, and static ports. Wheels, chalk the wheels and set the parking brake. Secure to anchored cables or dig a hole for each wheel. You might want to dig a hole for the wheel, let the air out, and then fill the hole in, along with tying the plane down so it doesn't go anywhere. Note, check your pilot operating handbook for brake system heat expansion problems. You might not actually want to set the brakes. Securing your aircraft outside. Control locks. Make sure your control surfaces can't move and flap around in the winds. Install internal and external gust locks. Avoid looping a seatbelt around the controls. This could set the controls in a climbing turn, which is exactly what the aircraft will attempt to do in severe winds. We've already seen that. Tie-downs. Always use tie-down rings on your aircraft, not the struts. Okay? Use nylon, Dacron rope, and chains. Don't use old manila rope. Try to tie down the plane in 45-degree angles. So for a review of what I've just done, the meteorological term for a hurricane is a tropical cyclone. There are 80 to 90 tropical cyclones a year. The size averages 300 miles in diameter. All tropical cyclones are unique. The storm's forward speed, if any, is about 10 to 15 knots. Although hurricane season is officially June 1 through 30, most hurricanes occur in the autumn during August, September, and October, with September being the most intensive. Most dangerous areas of the hurricane is in that right front quadrant. Most intense and violent weather in hurricane takes place in the eye wall. Storm speed must reach 64 knots or 74 miles an hour to be labeled a hurricane. The eye of the hurricane is usually calm. For a hurricane to form, the conditions must be just right. The movement of a hurricane depends on the prevailing winds, like the cork in the stream. Most fatalities come from landfalling hurricane, take place during coastal flooding, called the storm surge. Hurricanes do not form close to the equator because lack of rotational energy from the earth, we call the Coriolis effect. Thermal energy that powers a hurricane is primarily from latent heat. Physical processes are evaporation, condensation. September 10th is the most likely day statistically. Prior to radar and weather satellites, all we had were recording barometers, and the sun is the primary source of energy for all weather on Earth.
Wow, that was a tremendous presentation. Now, stay tuned because you're going to see the 4-digit code that will allow you to get credits for your WINS program. Again, we're signing off right now. This is the most exciting interview. Notice that I didn't say anything. Anyway, thank you so much, and we'll see you again in our next Plane Time show.